Hello everybody, welcome to another video lesson. We are starting a new topic on sequences and series. We're going to start today with sequences and convergence. After this video, we'll be able to evaluate different types of sequences and determine if a sequence is convergent or divergent. So let's hop right into our concepts. First things first, what is a sequence? Well, it's just an ordered list of numbers. That's it. Just an ordered list of numbers. It's not some random list of numbers. It's going to have some order to it. Take a look at this example down here. We have one block. We're adding one block to make two. We're adding one block to make three. Okay, we have some order to what we're doing here, right? We're not adding 3 blocks and then subtracting 4 and then adding 12 and then subtracting another 6 and then adding 100 and just randomly, right? So there is some order to what we're doing here with these lists of numbers. Now we have two types. We have a finite sequence with a finite number of terms, or we have an infinite sequence with an infinite number of terms. And you can tell here that you have an infinite sequence with this ellipsis right here, okay, a little dot, dot, dot right there. Okay, so here we have a sequence with 4 terms, 2, 4, 6, 8, and here we have a sequence with infinitely many terms, okay, 2, 4, 6, 8 are just the first 4, and it's going to go off for an infinite number of terms, okay. We have explicit formulas that we can use to define certain terms within our sequence. So we are going to be defining a sub n as a function of n, where n is just the numbered term that we have. So here, this block here that has, oh, look at this one that has 3 blocks in it, right? This is going to be our third term. So this we would say is a sub 3, right? Because this is the first term, 1, 2, and 3. So this is our third term here. Okay, and an explicit formula is going to define it as a function. Okay, so it's going to look like a function like we've looked at before. And we can use this to find the nth term of any nth term. So we could look at it to find the 100th term, the 1000th term of this sequence. And we also have recursive formulas where we're going to define the nth term using previous terms. Okay, that's important. When we're working with explicit terms, I don't need the 99th term to find the 100th term. I can just go ahead and plug in 100 for n, and I find the 100th term. However, for recursive formulas, we do need the previous term in order to find the term of interest, or the nth term. Okay, so there's an example of that. Okay, next concept, our Fibonacci sequence. This is often found in nature, so if you're ever given a problem with nature in it, you should be thinking Fibonacci sequence right away. And all that is all the Fibonacci sequences is a sequence where each term is defined with this by the sum of the previous 2 terms. Okay, so our Fibonacci sequence looks something like this. So I've got 1, there's no previous term with that, so our next term would also be 1. But now, in order to get the next term, I add these 2 1s, so I get 2. And to get the next term, I add the 1 and the 2, so I get 3. To get the next term, I add the 2 and the 3, I get 5, and so on and so on. And you guys have probably seen the Fibonacci spiral that looks something like this. This is often used in a lot of artistic settings. Last concept here of convergence and divergence. So we would define a sequence as convergent if it has a limit that the terms are approaching a unique number, okay, a unique certain number. So an example of that would be, if I have this, this sequence right here, we can see we start at 1. This is my term value here, and this is the number of terms. All right, so as the number of terms gets larger, okay, number of terms again is my horizontal axis, the term value is the vertical axis. As the number of terms gets larger and larger and larger, the value of those terms is approaching some value, right? It looks like it's approaching 0. So we would say that that is a convergent series, or sequence, sorry. And we would say it's divergent if the sequence does not have a limit approaching a unique number. Does not have a limit. So an example of that would be right here. Again, I've got number of terms, or the term number, on the horizontal axis, and on the vertical axis we have the term value. And you can see that it is, one, oscillating, okay, so it's never going to approach a certain single value, but also that oscillation is getting a lot larger, larger, and larger. So as the number of terms increases, we're not approaching a certain term value. We're just approaching really big numbers and really small numbers. All right, so those are our 3 concepts. Let's go ahead and get into some examples. Example 1, finding the next 4 terms of the sequence. So we have our first sequence here, 32, 16, 8, 4. What are we doing here? What are we doing from 32 to 16? Well, we are dividing by 2, right? And from 16 to 8, again, we're dividing by 2. From 8 to 4, we divide by 2. So we're going to use that pattern to go ahead and find the next 4 terms of our sequence. So I'm going to start with 4, divide by 2, get 2. I'm going to use this 2 and divide by 2 again, I get 1. Take that 1, divide by 2, I get 1/2. Take that 1/2, divide by 2, and I get 1/4. So the next 4 terms of this sequence would be 2, 1, 1/2, and 1/4. So that would be finding sequence terms. Let's go ahead and look at another example, finding sequence terms again. Find the first 4 terms of the sequence given by, now we have an explicit formula, right? We have a sub n defined as a function of n. So what we can do is just go ahead and start plugging in values. Find a sub 1 first, and then a sub 2, a sub 3, and then a sub 4, because it says the first 4 terms. So a sub 1, how this works is, since I'm looking for the first term, that's a sub 1, and I would just plug in 1 for n, which means that I would plug in 1 anywhere that I see n within my function. So this term counter here is what I plug in for my n value, okay? That's what we're doing here with our, as a function of n. So when I calculate that out, I get -9. A sub 2, I would go ahead again, just plug in 2 wherever I see n, and I get -2. A sub 3, I plug in 3 now, and I calculate that out to be 17. And a sub 4, that's going to be 4 cubed minus 10, that's going to be 54. All right, so our 4 terms of this sequence, first 4 terms would be -9, -2, 17, and 54. Okay, now with recursive sequences, if we're asked to find the 6th term of our sequence, notice, remember, for a recursive sequence, I need to have what? For finding a sub 6, because that's the 6th term, I need to have a sub 5. Now, if I were working back here with our, again, these explicit terms, I don't need to have a sub 3 in order to find a sub 4, right? These are more or less independent of each other. I don't need the previous term to find the next term. However, for recursive sequences, that's not the case. So if I'm asked to find the 6th sequence of each sequence, the 6th term of each sequence, I'm going to need the 5th, the 4th, the 3rd, the 2nd, and the 1st. So let's go ahead and find, we're given a sub 1, so we can calculate a sub 2 with that. And we can see that this is a recursive sequence because right here, this says a sub n minus 1. A sub n minus 1 means we are dependent on the previous sequence, or the previous term, for whatever term we're looking for. So a sub 2 would be -2, and then a sub 2 minus 1. So that's going to be -2 a sub 1. A sub 1 was 3, so -2 times 3 is going to be -6. We just keep doing that process. So for a sub 3, I would have -2 times our previous term of -6, so that's going to be 12. And then -2 times 12, that's going to be 24. -2 times that -24 is going to be 48. And a sub 6 would be -2 times a sub 5, which was 48. So it's going to be -96 for my 6th term. Okay, so you guys pause the video and see if you can't find the 6th term of this sequence right here. Okay, this is the process. Hopefully you got a sub 6 was equal to 39. Okay, 4th example here, Fibonacci. We have a tree, let's see, suppose that a stem on a tree must grow for 2 months before it is strong enough to support branches. At the end of the 2nd month, it sprouts a new branch and continues to sprout a new branch each month. The new branches grow at the same pace. How many branches will a tree have after 18 months? So if you are given a situation like this, the best thing you can do is go ahead and create a table, right? So the first row I have here is the months, 1, 2, 3, 4, all the way up to 18. And now what do we have? So at the 1st month, I have 1 branch the 1st month. It's going to take 2 months for that one to start to be able to support the growth of another branch. So after that 2 months, we see another branch come in, and then that branch needs to start growing. So we're only going to see 1 more branch come in on the 4th month. So you can see how we start to have this Fibonacci pattern where the previous 2 months are going to determine the number of branches on the current month. Okay, so we start to see this Fibonacci pattern, and yes, that's what we have. And at the end of 18 months, we have 2,584 branches. Okay, last example here, looking at convergence or divergence. We're going to determine whether each sequence is convergent or divergent. So we are given an explicit formula here, right? A sub n is equal to 64 over 2n. So we can go ahead and plug in a sub 1. Let's figure this out. Let's start plugging in some values and see what happens to our terms. Are they going to approach some number, or are they going off into infinity, or what's happening? So a sub 1 we see is 64 divided by 2 times 1, so that's going to be 31. A sub 2, again, we're just, instead of plugging in a 1 for n, I plug in a 2, that's 16. I plug in a 3 for a sub 3, I get about 10.67. And then a sub 4 is 8, a sub 5, we get 6.4, a sub 6, I get 5.3, and so on. And I just keep calculating these numbers, getting larger and larger. And you can see they're going down, right? But are they approaching a certain value? Well, in order to figure that out, you may need to plug in some larger terms here. So instead of just going a sub 14, I'm going to look at what is a sub 100. Well, that's approximately 0.32. Okay, we're getting a little bit closer to something here. Let's plug in a sub 1000. If I plug that in, that's going to be 0.032. So we can see here we are actually coming towards some number. We're going to be getting closer and closer. It looks like to 0, right? Our number is getting lower and lower and lower until we're going to eventually hit 0. So yes, we are convergent on this sequence, all right? Now our n value is greater than 1. I just wanted to make this point here. And we are never going to go below 0, right? There's no way I can make this 0 because a sub n is always greater than or equal to 1, right? So a sub n is always going to be greater than or equal to 0. That lets me know I'm never going to go below 0 in this case, okay? So that's how we can tell that we are divergent. Okay, go ahead and pause the video and see if you can determine if this sequence is convergent or divergent. All right, you can see here that we are actually oscillating between -3 and +3 for this sequence. So because that is the case, we are not approaching a single unique value. We are going in between -3 and +3, which means that we have a divergent sequence on our hands. All right, guys, that is it for this video. Good luck with your practice.